Hello, everyone. My name is Cohen from the International Centre for Neuromorphic Systems at Western Sydney University, Australia. And today I'm going to talk to you about the Astrosite, which is our mobile neuromorphic space situational awareness observatory. I'm going to tell you how we're using neuromorphic algorithms and cameras to do space imaging in a completely different way. I'm going to talk to you about the Astrosite itself, which is our containerized solution that uses these neuromorphic technologies to do things you can't do with normal telescopes and normal cameras. So why solve this problem? Well, we've been launching objects into space for 60 years now, and space is getting pretty cluttered up there. And this is a growing problem because we're reliant on space for almost every aspect of modern life, from communication satellites to GPS to critical defense and weather systems, for example. The problem is, of course, that every time we put a satellite up, the risk of collisions increase, and collisions in space can be catastrophic. These objects are moving really fast around the Earth. And if we don't do something soon to look after our infrastructure, we could have disastrous consequences. Of course, to the extreme of something called the Kessler effect, where one satellite collides into another, sends high-speed debris in all directions that hits other satellites and destroys them, creating this debris field that locks us into Earth. Now, of course, that's the worst-case scenario, but these are things that we have to start thinking about as we put more and more satellites into space. Just think of these mega constellations that SpaceX, for example, are thinking of putting up. So the trick, of course, is that in order to start cleaning up space, which is something we don't really do, or even just policing and regulating it, we have to know where everything is and how bad the problem is. And that's when neuromorphic cameras can help. By putting these on telescopes, we can absolutely detect and track satellites in a completely different way and unlock new ways to do what we call space traffic management, space situational awareness, or space domain awareness is the new term for it. So let me start by talking to you about our team. So these are the people who really made it all happen. And the team since then has grown. We have a whole bunch of new people working on algorithms and ideas and applications and refining the technology. But it's this cool group of people over here and our funders, the Air Force and Plan Jericho and DST, who really took the idea from literally a sketch on my boarding pass like this. This is the real thing, actually. This is how I pitched it. All the way to this, a fully functional containerized observatory at the Avalon Air Show last year. We did this in a couple of months, which was fantastically incredible. And it was just a testament to the fantastic people I work with that we managed to do this. And it wasn't easy. We had to fabricate a specialized shipping container with a sliding roof. We did it literally first time we'd ever figured out how to do this. We had to figure out if everything fit. Telescopes are actually quite complicated. They move in strange ways. And for people who work in space, we haven't got the best spatial awareness. So we had to actually make little 3D models and move them around to make sure everything fitted. And after a few months of really hard work, we landed up with this. This is the Astrosite. It's a mobile telescope observatory built into a shipping container. The roof slides. Right? It's a mechanical sliding roof, and a scissor lift lifts the telescope up. And essentially, you can put this shipping container down, plug it in, slide the roof off, raise up the telescope, and do space imaging straight away. And the great thing about building into a shipping container is that there's an entire industry built around moving these things around. There are ships, there are trains, there are boats. This is a standard shipping container that can be moved relatively easily, which means we can pick up our observatory, move it easily, and put it down somewhere else. I'll show you how neuromorphic technology lets us do that, how it makes us less sensitive to the motion. I should say there's also a little office in there, so we can actually conduct experiments from in there, and I'll show you what it looks like inside. But the question really is, well, what does neuromorphic cameras do to help us with space imaging? Well, it turns out that space imaging is actually a really good application for neuromorphic cameras because it's all about contrast. Space is dark, and we're looking for bright things on a dark background. We're also looking for things that are very fast, they're moving quickly. And that's where integrating cameras become a bit of a problem. So what we found is that we're really good at capturing things like satellites with these cameras. Not so great at taking pictures, but then again, if you want to do tasks in space, you don't really want photos. And what we found is that we can also use these cameras. So we're leveraging the high temporal range to move the cameras. We can move the telescope and image whilst we move. And that opens up a whole range of really interesting possibilities, such as being able to track objects and follow them. We can also use the high dynamic range of the sensor to do a lot of this during the day. Now, if you think about a telescope observatory, if you can only operate at night, you're only working half the time. If you can operate during the day as well, you've doubled your efficiency, which isn't bad for a day's work. On top of this, we can also use the fact that there's actually less data. We don't need all that black sky. If it's dark sky and nothing's happening, we don't care about it. If something shoots through the field of view like a satellite, not only can we detect it quickly, but we can start tracking it straight away. So what I'm going to show you now is some telescopes. This is the first set of telescopes we ever used for these experiments. This was done in Adelaide with DST, and I really like these because this is where it all began. And if you look at the left-hand side there, you'll see two telescopes. They're actually on a mount that can pivot, much like the one on the right-hand panel there. So we can point accurately at the sky. And the two telescopes are both-sided, so they're looking at roughly the same thing. What you might notice on the top telescope is that big camera at the back. Now that's a finger length instrument astronomy camera. It's a beautiful camera, but specially built for space imaging. It's actively cooled. It's a real high performance, well-built camera. If you look at the bottom telescope, you'll see, in fact, one of the old ATIS prototype cameras hanging off the back there. That's a shoddy event-based camera that I put together myself. I say shoddy because you can actually see the screws hanging out of it. But essentially, I like the contrast here, which is to say, this performance we're seeing is with a camera, an event-based camera that wasn't built for this task, compared to an astronomy camera that's specifically for that task. If you look at the middle panel, you'll see that the top telescope with the astronomy camera has this aperture, which is just a cardboard box with a hole in it. Now, we needed to use that aperture in order to look at bright objects like Jupiter, which I'll show you in a second. Whereas with the event-based camera, we never have to touch the optics. We use the high dynamic range of the camera, and we can see not only just at night with this, but during the day as well. So sort of focus and forget. And that's really important if you want to put these cameras in remote places and not have to worry about changing lenses or having mechanical systems to do that. We then moved on to this 3-telescope setup that you see to your right-hand side. And that one has actually both a ATIS and a Davis, so we're comparing cameras and how they work. I'm going to show you the first results we ever got with an event-based camera on a telescope. And this is Mars. With an event-based camera, this was a really big deal because we had no idea what we were looking for, what it would look like. And in fact, you might notice it bumps up and down a bit. That's because we were excited and jumping up and down next to the telescope. But you also might notice there's this oscillation, a sort of circular pattern to it. And that turns out to be atmospheric scintillation. And that's a really interesting phenomenon in itself. And in fact, we have a project to explore the applications of these cameras in adaptive optics, because we're capturing this really fast. And we actually use that to compensate for the motion of the atmosphere and do better astronomy. So from this, roughly around the same time that night, we're looking at a different part of the sky completely randomly, just staring. But all of a sudden we saw this come through the field of view. And we looked at this and we thought, what is that? Started a whole bunch of lively debates, and after a while we realized it's a low Earth orbit satellite. And that was kind of the aha moment for this work. We're like, oh, this is interesting. This is something you can't do with a normal imager. So this really led to the whole project and ultimately to the Astrosite containers I'm going to show you in a second. So what we did next was then point the telescope specifically at these objects. So this is what it looks like. If you look on the left, you'll see a frame-based representation of the data. And you can see why it really doesn't do it justice. You can see it's just a dot on the frames or on the frame-based rendering. But if you look at the spatial temporal data with time as the vertical axis, you can see it's actually a real rich stream of events as we move the telescope to keep this satellite in the field of view. What you'll see flying through the field of view are stars. And there's actually a lot of information in that stream of events. Sometimes we can tell things like if the satellite's tumbling. And as we explore more and more, I'm sure we'll find out other things we can characterize and determine from that event stream. Now I'm going to show you something slightly different now. I'm going to point the camera at the Jewel Box cluster, which is a beautiful collection of stars. If we look at them through a telescope, you'll see that they're actually quite colorful. And what you'll see here on the far left-hand panel is a frame-based output from a camera looking at the Jewel Box cluster. In the middle, you'll see the event-based output. And what you'll notice with the frame-based output, as you move the camera back and forth, the stars disappear because you can't see them when you're moving, you get motion blur. But on the event-based camera, it's exactly the other way around. It's actually hard to see the stars when they're stationary, but when the moment you move the telescope to back and forth, the stars jump out. And this is really where I see event-based vision and conventional cameras for astronomy working together. They're complementary, not a replacement for each other. And this is really where we see all the applications for event-based cameras and being able to image whilst you move, use that to your advantage. So let me show you what it looks like inside the Astrosite. Here's me actually grabbing that data the other day. You can see it's quite a little bit of a command center. This is inside the Astrosite with the telescopes just off to my right. It's actually quite a nice, comfortable place, both for the desert with an air conditioner. But of course, there's no reason why I have to operate it from inside there. This is built to be remote after all. So sometimes, on a nice day, I might choose to sit outside and operate it from here. And of course, there's no reason why I have to do it on campus. I could do it from home. Or, for the same token, I have someone in Europe do it during office hours for them in the middle of the night for me. So this is the whole idea. Eventually, and this is where we hope to be soon, is to have these completely autonomous, where they collect data and just send us the results. We tell them what to look for, and they come back with information that we send to a central point. And if we only capture what we need, the amount of data we have to send is far lower. So now I'm going to show you Jupiter. Here's the telescope going up, and you can actually see Jupiter just to the top right of that image. There's that really bright dot in the sky over there. Now, when you point an event-based camera at that, here's the frame-based output of Jupiter and the event-based output. And you can see it's quite beautiful. You can actually see 3 of its moons. And what you'll notice is that as we move the telescope on the event-based camera, it's really nice and smooth. You can see the stars moving, but you can see on the frame-based camera that it blurs. This is the problem with stability. When you move conventional cameras around, you get this blurring effect, and that makes it really hard. In fact, most satellites and conventional images look like streaks. Now, I'm going to do something that's going to upset any astronomers in the room, so please, if you are an astronomer, I would suggest looking away now.
So this is what you absolutely shouldn't do around a telescope, just for the record.
So this is the idea of using near cameras to get motion insensitivity. Essentially, not only does the motion not really bother us, in fact, we can actually use it to our advantage. It helps us see things. So now you can understand why when we put these telescopes somewhere where the ground isn't necessarily stable, or we're near to a road or on top of a building that vibrates, it doesn't really harm us. In fact, if we know something about that motion, if we can measure it, for example, we can use it to extract even more information from the scene. So it's a whole different way of doing imaging. And that's something that's really exciting. Now, I haven't talked so much about the algorithms that we're using it, but I'll give you a little taste of that. So what I'm going to show you next is probably the pinnacle when a whole bunch of different technologies come together with these. And what we're doing here is we're tracking a satellite like before, and that's in that red circle over there. It's a bit hard to see, but it's there. And we're moving the telescope to keep that in the field of view. And what you're seeing in that top left panel is all the stars moving through the background. Now what we can do is take those stars and build this beautiful star map they see in the background of that image. That star map we can then use to figure out exactly where in the sky we're looking. You can use it to do the place solving, the astrometry, and figure out exactly where the telescope is pointing without having to use expensive software or very calibrated mounts. This means in the future we're going to use really low power, low complexity hardware rather than using these expensive telescope mounts to move the telescopes around, and yet still figure out just from the information that we're seeing exactly where we are whilst we're moving. We can then use that information to infer how the telescope is moving, and what we do is compare that to the actual known motion of the telescopes we have to figure out how well we're doing, and it's actually extremely good. And we can also do other things, for example, like take 2 cameras on 2 different telescopes with different fields of view and have sort of foveated vision. We can go off and follow objects of interest in the sky. There's a whole range of possibilities of what you can do with these event-based cameras on telescopes that you cannot even comprehend or do with a conventional camera. And that's the really exciting applications for this technology. So what I'm going to show you now is just a little sneak preview of what we've just built, which is our second Astrosite. This is Astrosite 2. You might notice the colors are inverted. What we've also changed here is changed the mount around. If you look on the right-hand side there, you'll see that as opposed to the previous mount, this is what we call an azimuth elevation mount. And that'll give us some really interesting abilities. For example, it can move a whole lot faster than the previous one. It's also good for tracking other objects in the sky, like planes. And what we plan to do with this is we plan to put these 2 astrosites in different parts of the country and start synchronizing them to do ranging. So not just figure out where the satellite is, but how high above the ground it is. And that's something that's extremely hard to do optically. And this is essentially where we're going to put one in Adelaide, one in Sydney, for example, and use them together to operate a network. Our goal, of course, is to expand this network across Australia and build a really interesting and fantastic space situational awareness or space domain awareness system across the country. So what I'm going to leave you with is a fantastic view of where these things go. This is the deserts of South Australia, where we go once a year to test these sensors in a real-world condition. This is in the middle of the outback, in the middle of nowhere. And this is, in fact, the original telescopes that we did the recordings with. But this is where we're going later this year to test these cameras in the sort of beautiful outback part of Australia. So thank you so much for your time. Please, if you have any questions, send me messages on Slack or on chat, and I'm more than happy to answer them. We may organize a question session if there's lots of questions, and I'm more than happy to talk through them at a later time. Thank you so much for your attention. Have a good evening.